Ladies and gentlemen, dear guests, dear colleagues, my name is Sebastian Werle. I'm the Vice Rector for Science and International Collaboration here at Silesian University of Technology. I'm very happy to welcome you to the third International Conference on Priority Research Areas, the main event of the Science Day here at the University, Silesian University of Technology. I welcome everybody which are here in the room, also all of us which are joining us online. Let me begin by offering a very warm welcome Professor Luisy Cabezy, our opening session keynote speaker, highly cited researcher, and expert in the building efficiency and also thermal energy storage. Professor Cabezy, we are honored that you are with us today. Thank you very much. I would also like very warm welcome all distinguished speakers. Especially, I'd like to welcome Professor Paul Franks from Lund University. Professor Taras Oleksik from the Oakland University. Professor Rosella Tupler, University of Modena. Dr. Jennifer Sargent, Babelfisk, Sweden. Professor Małgorzata Oczko-Wojciechowska, National Oncology Institute in Gliwice. Profesor Jerzy Stanisławski, Poznań University of Technology. Professor Przemysław Juszczuk from the EMAC Institute. Maciej Gdula, Skill.org. Dr. Ximin Liu from Department of Energy and Mineral Engineering, Penn State University from USA. Professor Lucio Zavanella, Department of Mechanical and Industrial Engineering, University of Brescia, Italy. Professor Krzysztof Pitz from the Poznań University of Technology. Professor Alain Kelzart, University of Lorraine, France. Professor Louis Pitet, Hassel University, Belgium. Professor Malte Borgers, Eindhoven University of Technology. Professor Vinit Parida, Luleå University of Technology, Sweden. Professor Pierluigi Siano, Electrical Power System. And also I'd like to warmly welcome all highly cited researchers, Eureka Pro-University Alliance members, Polish Academy of Science Scholars, Łukasiewicz Network, and many universities in Poland and abroad. Welcome everybody. I would also like very welcome the academic community of our university, vice rectors, deans, vice deans, chairs of the discipline council, priority research areas coordinators, students, doctoral students, administrative staff members. Thanks for coming. Thank you very much. And to officially open, I now have the pleasure to inviting the rector of our university, Professor Marek Pawełczyk. Please, Professor.
Good morning. It's my great pleasure and honor to welcome you all for the third meeting of this kind, Science Days at the Silesian University of Technology. Many of you perhaps are for the first time at our university, and I believe that you will have time to visit several our facilities and perhaps visit some laboratories, but what is most important, to meet people. That's why, first of all, we guaranteed for today very outstanding guests. I would like to thank Vice Rector for inviting and welcoming the outstanding guests. They are representing different universities. Some of the universities are collaborating with SUT in the frame of Eureka Pro European University, but they are also representatives of many other universities from different parts of the world. That is very important that, first of all, we have connections and we have collaboration with so distinguished individuals. And I understand that when you decided to come to our university, you also thought about what is being done at our university. And I would like to tell you that Salesian University of Technology is one of the 10 research universities in Poland. And this status was achieved based on a thorough competition. A number of Polish universities were evaluated by international panel of experts, which was composed of 15 very outstanding specialists in the field of higher education and science. These were former presidents, rectors, or people responsible for the education systems in the countries. And they, first of all, trusted our university, the strategy of development, and dedicated that status. We are holding this status, and we are going to be, I believe, we can extend it for the next 6 years. It gives us very rare opportunity because we receive, first of all, the prestige. The second is additional funding, and we can dedicate the funding how we defined our plan. And different universities approach this idea in different ways. But the idea of our university was just to dedicate about 95% of the funding to human capital, because we believe that, first of all, changing the culture of the university, allowing our staff to reach bold goals, to establish some connections, to visit different universities, and have new scientific friends. And after a few years of implementation of this IDO program, I think that we totally changed over that time. And you can meet very good specialists at our university. You can meet also nice infrastructure, which is really special, really unique, because when we have appropriate people, they can also efficiently apply for the infrastructure. We defined, when applying for this status, 6 priority research areas. And this conference today and tomorrow will be oriented on the priority research areas. There are 6. And they were identified based on our competence, based on our connections, collaboration, also infrastructure, collaboration in terms of the scientific collaboration, but also industrial collaboration. And one of the priority research area will be explored today by the panel discussions, but also the plenary presentation. So please take the opportunity to make new connections, to establish new ideas, and hopefully also new projects. Having at our university so distinguished guests, among them they are highly cited researchers, ERC grant holders, and people who are very much recognized in the field, we, first of all, can take this opportunity. So we'd like to learn from you how you plan your research activity, how you collaborate, how you are working. So apart from your presentations, which will be dedicated to the field you are working with, we would like to also learn from you how you can achieve so big results. And that's what, that's why we would like to meet you and learn from your experience. Thank you very much, and I wish you very successful collaboration. I would like to now welcome Professor Cabezy to give a plenary presentation. And thank you very much for coming to the Salesian University of Technology. You are mostly welcome. The floor is yours. Thank you.
Somebody would tell me. Thank you. Okay, thank you. Good morning. First of all, thank you to the Salesian University of Technology for this invitation. It's really a pleasure to be here and an honor, and especially to open this conference that it's very multidisciplinary, and I think it will be very interesting for all of us. And actually, my talk is a bit about this. It's a bit how important is multidisciplinarity and to open also our minds into seeing that, to me, what we do need to go a little bit further on to technology. And that's why I got interested in sustainability and also social aspects of what we do. I always say that it doesn't matter how great is our technology and how good we develop it, that if at the end the final user doesn't understand it and doesn't use it correctly, our work is worthless. And this is especially important in the built environment where the final user will not be a practitioner or an engineer, but it will be all of us, people living in our houses. So my presentation is a bit too long. I will go fast with some slides just to give you the message. So first of all, I have to, So I'm a full professor at the University of Lleida. University of Lleida is a small university where I joined it 25 years ago. So a lot of what has happened is just because I'm getting old. It's nothing else than this. But it's true that I love research. I love my job, and also that's what it makes what I do fun, and therefore I get the spirits to continue on doing this. And I think this is the message also for the young ones, guys that you are here. If you like your job, then it's when you can make a difference on what we are doing. So as I said, Lleida is a small city. So I work at a small university in a small city, but still, today it's a university city because around 10% of the people living there either study or work at the university. As you can see, it's halfway between Barcelona and Zaragoza, which is in the way to Madrid. It's still in Catalonia, but very much inland. And it's not really a touristic city, so it also makes it very nice to live in and to work there. When I joined the University of Lleida, engineering was just starting, and we created this research group where what we wanted to do is to, of course, be the reference university and research in the city of Lleida, where there is a lot of industry. It's not very well known, but agro-industry there is very big. And to avoid that, they had to go, for example, to Barcelona to find this knowledge. But we always had this idea of also becoming known internationally, so that what we do would benefit from what is done abroad and also have an impact there. I like very much this image in the bottom because as you hear, most of you are engineers like us, you will understand this. I really like having new ideas and going to the lab and testing them and see if my crazy ideas work. So we like to work here in low terrals, but as being engineers, we also love to go to the industry and to really know that what we are doing, it gets into the industry and it's something that it gets into the market. The photos here are not by chance. We actually worked many years in the concentrating solar technology in Spain when it was developed around 15 years ago. And today we can say that all the thermal energy storage tanks that are built worldwide have a little bit of our input, of our science in them. So what do we do today at GREIA Research Group? GREIA stands for Energy and Artificial Intelligence. In Spanish, EI is Inteligencia Artificial. So we say it in the other way around. But actually, that's the idea. It's a joint of two research groups previously, one working on energy, where thermal energy storage is our flagship. But we also have, today, 60% of our academics are from artificial intelligence. And I always say that they do their weird things, they do their theories, but half of them work very closely to us to use the artificial intelligence in what we do every day. From control strategies to design of storage tanks to selection of materials. And they still kept telling me all the time, Luisa, we have to meet, we can do much more for you. And we also work in chemical engineering. When you work in thermal storage, you will see later, if you don't do materials, it's a little bit difficult to be there. So now, why is thermal energy storage so important in the energy system? At the end, I like to always start with this slide because even though it's obvious, a lot of people forget that the energy system is not only the production of energy. Some people work in that field and they always focus in how to produce energy. It's not only using the energy in different areas, but it's also, transporting the energy from where we produce it to where we use it. And actually, thermal energy storage has or can have an impact mostly in the production and in the demand side. But when you do this, it's very different the way you use this technology. We don't have to go too deep into this. We all know the energy today, it's really one of our main concerns. We are growing on energy demand, even though we are doing big efforts to decrease our per capita energy use. We still, more and more people, more and more buildings, more and more industry, and therefore this is a big concern. Also in Europe, we are short in energy and we have to import a lot of it, but in some parts of Europe, more than others, but I think all of us have a little bit of renewable energy potential. One of the goals of the EU is to decarbonize our energy system, and that's why we have a role here and where we can make an impact. As you know, renewable energy is not constant. We have it when we have, and we have to use it when we need. And this is why energy storage is so important. For us, thermal energy storage also is very important, but I always say that it's the forgotten or the unknown energy storage technology. When we talk about energy storage, everybody immediately thinks about batteries. Today, even other technologies like supercapacitors, flywheels are there, but most people don't know or don't remember that thermal energy storage also can have a key role in this change. We can use it for just storing the energy and to use it in a later stage. That is what usually it's known for, just to change, let's say, the time of use of the energy. But we need to remember that we can also change the power, we can also change the place, so we can transport energy, and we can also change the temperature. A lot of times linked with a heat pump, but sometimes not even, you don't even need the heat pump. So really thermal energy storage is a technology with a lot of potential, and that can help us, as I said, both in the supply side, but also in the demand side. This is also kind of obvious, but a lot of people forget about it. We need a thermal energy storage tank. We need a place to store this energy, and this is one of the issues that we are always working with. The size of this tank, it will depend not only on the technology, but also on how or why you need this technology. So if you need it for a short term, it will be smaller. Maybe if you use a technology like we will see thermochemical, it will be smaller. But maybe if you go to seasonal storage, which is something that we are very interested in, it will be bigger. Also, from an engineering point of view, it is very important to understand that for these systems, you need to charge and to discharge this storage tank. We need to remember that storing the energy, the material, will give you the energy density, but the way you charge and discharge will give you the power. So how fast can you charge or discharge this tank? And I always hear people telling me, you need to have a lot of power because you need to charge and discharge. That's not always true. For example, in the built environment, as we will see later, if we use the storage in the walls to keep the room at a nicer thermal comfort, then you don't want to discharge fast. On the contrary, you want to discharge very slow. Okay, so this is something that always we need to keep in mind, that there are these two aspects, and also that, as you see, this is very multidisciplinary. When we work on energy density, we work at material level. When we work on the power, it doesn't matter if it's fast or slow. It's more a mechanical engineering level, but if you put it in the built environment, then you talk with civil engineers or with architects. So at the end, as I said, many different disciplines are involved in this technology. This is the most known application of thermal energy storage, especially in the built environment, and it's actually to shift when you produce the energy to when you use it. We can link to renewable energies, as I said before, but you don't need to. You can also use other sources of energy, but one of the ideas is, for example, to decrease the peak of the cooling demand in our buildings. Even today, in countries like Poland, this is becoming very important because we are realizing that cooling is starting to be one of the future keystones of our world. Until now, people were very focused on heating, but today we also all use very much cooling. But the problem with cooling is that it's very much energy demanding, and also usually we use it at a given time of the day. For example, in summer, you would need air conditioning mostly at lunchtime. If all of us switch our air conditioning system, then we have these peaks in the energy demand that sometimes our energy grid cannot withstand it. So that's why we are using, for example, thermal energy storage, where you can produce this cooling at off timings, and then you use it during the day. How do we do this? The easy technology is just you produce ice during the night when you have excess of electricity, and then during the day, you only have to melt this ice to have the cooling during the day. I think that for us, this is known, but to me, what is very strange is that there is a lot of industry using this technology. For example, the dairy industry, but if you ask them, do you use thermal energy storage? They will tell you no. Do you store energy? No. But they are doing it because they are producing ice at night and then using this cooling during the day. That's why I started saying that this is an unknown technology or forgotten technology. So which technologies do we have here? I think that the slide is heavy and it doesn't come. Yeah. So there are three main technologies in thermal energy storage. The first one is the most known one, which is sensible energy. This is when we heat a material to store energy in it. Okay, so the technology here, remember, is just heating up, for example, heating up water to use it at a later stage. The second one, that it has been attracting a lot of interest in the last 20 years, is latent thermal storage, is when we use the phase change of a material to store energy. The example I gave before, ice, this is latent thermal energy storage. Okay? Why do we use this technology? Because we all know that to melt something, you need much more energy than just to heat that up, so you have more energy density. Okay? So with the less amount of material, you will have more energy density. These materials that are used like this are called phase change material, PCM, so somebody of you might have heard of them. So then you will ask me, okay, if we have ice, that's it, we already have it. The only problem is that here you get the energy at the temperature of the melting or the solidification of the material. With ice, this constant temperature, it's 0 degrees, and you cannot change it. So to change it, you need to change the material, okay? And you need to have other ones. For the built environment, we work 20 degrees C, 30 degrees C for thermal comfort. We work at 60 degrees C for hot water. For industry, we are going much higher, and actually discussing with this morning, I have a project with one of your colleagues sitting here with us where we are trying to use metal alloys as phase change materials for the industry, and we're working at around 300 degrees C. And the last technology is thermochemical, and here it's where we use either sorption or chemical reactions to store energy. So really here we are either by physical means, so with sorption, or with chemical means, with chemistry, breaking up a molecule to store the energy, and then when we put these two molecules together, we retrieve this energy and we can use it for our application. Here we have a much more energy density, but also the process here, the technology is more complex, and it's more into the development stage. So one of the things that I would like to highlight is that going from sensible to thermochemical, it's less mature, the technology, and also usually the systems are more complex, okay? One of the mistakes we usually do is that we compare the energy density at material level, but that's not fair for the technology, because maybe at material level, thermochemical is much more energy density, but since the systems are more complex, it might be that the difference is not so big compared to the other two technologies. I will go fast now because I have a part now where we talk about applications, but I would like to go more into the social part, that it's more the topic of the call today, and so that you see a little bit more of this interdisciplinarity. So here are the examples that I was saying. If anybody's interested, you can either ask me or the organizers for the talk. We can share this presentation. As we said, sensible storage is used with water, but also is used very much with solids, either at industry level or even in the buildings. Using massive buildings, it's really using thermal energy storage also, because we're storing energy in the building envelope. There are technologies that are mature and very much used in some countries like the Netherlands or Denmark or even China, where they use underground thermal energy storage using the underground to store energy, okay? I already mentioned the thermal energy storage in concentrating solar power plants, where they use molten salts at 300, 400 degrees C to store energy from the sun. These huge things are actually molten salt tanks. So they have around 4,000 tons of salts there to store the energy and to produce then the steam to run the turbines to produce electricity. This was, to me, it's very interesting to know that this was starting to be developed in the USA in the 80s. And then it was finally kind of developed together with them, but mostly driven by European funding in the 2000s, and today it's a commercial technology. Water tanks, of course, they are coming back today because of our change of the energy systems at home. In Spain, we use them today to store solar energy in thermal systems. In the UK, for example, they use them because they use mostly electricity to heat their water tanks, and they need to, because also because of the peak demand, they use water tanks to get showers. For Latin, what we discussed before, it's not only about energy density, it's also about having this, you recover the temperature at a given you recover the energy at a given constant temperature. Ice storage, we already discussed this a bit. And then with thermochemical, again, remember that these are two different technologies. I always say I don't like the name thermochemical. I prefer to talk about sorption and chemical reactions. And then applications. I already mentioned most of them, and that's why I will go fast through this. Today, the main applications on thermal storage are the building ones, where you can put energy storage in different ways in your building envelope and just let it go with the climate. This is when you talk about passive systems. You can then intervene with, for example, fans to discharge these storage systems, and then it's when it comes active. Or you can even join them in your already active systems, for example, with the domestic hot water, but today one of the hot topics of research is with heat pumps, of course. At high temperature, solar cooling was a very hot topic around 20 years ago. Today, it's not so attractive because to do solar cooling with thermal storage, you compete with photovoltaics. Photovoltaics with heat pumps is cheaper. Today, what it's a very hot topic because the industry is asking for it is industrial heat, and especially recovering industrial waste heat. And then also we already discussed about CSP. And then, you know, actually thermal storage is used in many other applications where we don't even know. As you will see later, I have a slide on this. So let me go fast with this. I just want to, I should have cut this out. We did this paper already 4 years ago on the state of art of thermal energy storage. We wanted to know what was going on, to see what were the research gaps on this. And at the end, a bit this is what I was saying, where this energy storage is used. And you see that most of the words here, we already discussed about them. Maybe not in the applications, but here you see that artificial intelligence, again, it's coming up with one of the already topics doing research on it. PCM have been always a big topic on research. I think people like it a lot. And because it's still not in the market fully, we could discuss why this is happening. There is a lot of research on this. Of course, today, hydrogen storage is booming, and when you discuss about thermal storage, you also find linkage with hydrogen storage. In the application side, we already saw some of this, that it's coming up here. Insensible thermal energy storage, again, when you talk about industry and high temperature, one of the techniques to use it is with packed bed, and this is also a very hot topic today. And here with these colors, with this technique, with it's called bibliometrics, we can see what is older and actually what is newer in the research. And in the yellow is the ones that are newer, and in blue is the topics that are older, okay? And this is what we use to find these research gaps. And we were trying to see, okay, which words come here in yellow, okay? And then also which ones we don't find them at all in the literature. And here, for example, we already see smart grid. I know there is a session on smart grids in the conference. And as you can imagine, thermal energy storage also has a big topic and a big role in the smart grids. Actually, energy communities are starting to be something very hot in Europe, and energy storage is one of the ways to help into sharing energy, for example. And the bottom part is more about heat transfer. I said that in thermal energy storage, you need to charge and discharge your system, your tank, and then everything related to heat transfer also is very important. But we also see bio-based PCMs. And here is where we start seeing something related to sustainability, that it's not only linked to renewable energies, okay? So when we talk about bio-based PCMs, is, okay, if I have to need a material where to store my energy, one of the things that I want to do is that this material is also sustainable. And this is why bio-based PCMs are one of the topics that are being studied today. And this is what I said, that also this is very cool, okay? We need to go a step further and start thinking, first of all, as I said, okay, if I have a material, it should be sustainable, it should be environmentally friendly, but also the social aspects. And this, in my research group, we started to work on them a few years ago to see why is the technology really not getting into the market. And we think that it's not only because of not enough knowledge, it's not only because of the cost, we also think that there is a matter on social acceptance. And this is what we try to study, and what I'm going to present here a bit fast, but that you see why we are doing this and why this is very important. And I think this is important in any technology that we develop. So I already said the two main applications today for thermal storage are the building and the industrial or power applications. Most of these, the difference is the temperature. Okay, in the building applications, we're talking about 20, so room temperature up to 80, sometimes 120 degrees C. If you talk about air conditioning, you can go a little bit lower, so to 7 degrees, maybe 0 degrees C. In industrial applications, we either are in the very much cooling side, so we can go to -100, or into higher temperatures where the industry needs heat for their processes. We started to work very much at material level into finding sustainable materials to substitute what already was used. For example, already we published in 2012, so probably we started in 2010, to try to use waste from wherever in our systems. Here we were using rubber crumbs. You may know this is a waste from the tires from our cars. And we were using them in buildings. In this case, it was in green roofs, substituting the drainage layer in the green roofs. We tried them, as you can see in the lab, and also in small trays, but also, I'm running out of voice, sorry, I have a little bit of a cold. Yesterday was 25 in Spain. Here it's, so my body also not adjusting very well, but anyway. So I was saying that we try this technology not only in the lab, but also in kind of real buildings. These are buildings that we have in our, well, it's not in the labs, but in the university area, where we have buildings like this, that they are 3 meters, 3 meters, 3 meters, so kind of a small house-like cubicles, where we test all these technologies. And here we implemented real green roofs to try these new materials. In another, this was actually a PhD that we developed also back then, where here we were trying to develop a new material for acoustic properties. Okay, when you have, this material is a layer that you put in the walls to really avoid noise to go from one side to the other. Probably this room has it, because usually when you have rooms like this where there is speakers, you need this. And to achieve this acoustic barrier, they use high-density materials. So working with the University of Barcelona, they were telling me, why don't we use, instead of any material, really waste from the metal industry. Okay? But when we were discussing with them, they asked me, but Luisa, can we also get some thermal properties to this new building material? And then we started to work with them also to include PCMs in it, so to give it this thermal inertia to the material. Again, we developed the material, we did all the acoustic stuff, we did all the thermal characterization, but then we actually worked with a company in nearby Barcelona, where they were producing this, so that they were really scaling up our material and seeing if they could produce it. And we also tested it in buildings. This time it was in an inner wall, and we really tested if, again, the acoustic and the thermal properties of the materials. It just sometimes it takes long because of the photos. Okay, similarly, we were trying to put waste materials in ram earth. Ram earth is a construction system that was used in the past, but in Lleida there are still a lot of ram earth buildings that when we talk about refurbishing, some people are just demolishing them and building up, but if you want to refurbish them, you need to work with this. And we wanted to substitute the typical straw, or even today, people are using cement for this ram earth to give it more structural properties. But if you put cement in the ram earth, your sustainability is gone. You cannot reuse this again. You cannot say that this. So that's why we added different materials. Even you see waste from olive production, which in Spain is big, rubber crumbs again, polyurethane. This polyurethane comes from dismantling refrigerators from home. Okay, so, and then we try to see the behavior of this, again in the lab, and if it does go. Yeah, so in the lab, but also in kind of real buildings, and use it and compare them to other buildings built with bricks and see the behavior of this material. we have done this also with algae. Seagrass is an algae. Actually, this comes from Sicily, from Italy. This is the algae that they take out from the beaches in summer so that we can go there and swim. And they don't know what to do with it. So we were also trying to add this in the building materials. We were trying to put lignin coming from biogas production in gypsum. All of this, I go fast. Everything is published. That's just that many examples of using of byproducts here in mortar to increase the thermal conductivity. Here, actually, for me, it's very interesting because this is a collaboration we have with Tunisia. They have a lot of textile industry. All the industry that we moved out from Europe, now it's Northern Africa or in China. And they now have the problems we had in the 80s. What do we do with all our waste? So this is a lady that she's coming to my lab, and we are adding textile waste. It's cotton, but also other textiles in mortar to be used, but also we include their phase change material to give both insulation and this thermal inertia. And we're having quite good results. Actually, I presented this where I met Angelina in Sinnercrete. I presented this work there. Another topic we are working with also, it's high temperature concrete. So here, we want to use concrete for storage at temperatures higher than 300 degrees C. You may know that normal concrete withstands are up to 400 degrees. That's why when there is a fire in a building, the building drops because the concrete just cannot withstand temperature. So in my lab, we have developed a concrete that can withstand 700 degrees C. We have done this by changing both the cement. We don't use Portland cement, but silica aluminum cement with different aggregates. Now, this concrete can withstand 700 degrees, so it can be used for CSP, but also for industrial applications. But all the aggregates we use here, we try to use only waste from different industries. So again, looking at the sustainability and trying to do the circular economy in our developments. So that's why we came to circularity. We need to start thinking that everything we develop has this circularity issue. Again, I don't want to go to too much detail here, but to me, when I sit with my PhD students and they give me an idea, I tell them, okay, but when you develop this new material or this new system or this new building concept, are you thinking on, first of all, not only using today waste, for me this is not enough, but also what is it going to happen to this at the end of its life? Okay, so if I have material, can I reuse it later? That's what I was saying before. If I put cement in ram earth, I cannot reuse it later. If I have a new storage tank, can I dismantle it at the end and reuse it again? And this is the concept of circularity. And I think we should all look at this, even if we work only at material level or developing a new model for a new energy system. You always have to have in your mind thinking, am I going to be able to reuse it later? Am I using raw materials that are either bio-based or that are, if possible, byproducts from another industry? Of course, if you use energy, you want to use renewable energy. And this is the concept that I wanted to bring in the talk, that anything that we do at technology level, you need to keep this in mind. How are we going to implement this and reuse it later? So I go fast with this because this is just, and of course, when we do this, at the end, we do this environmental evaluation, which is based on life cycle analysis or life cycle assessment. But to me, LCA is just a tool to measure the impact. It's not a concept by itself. The concept is the circularity, okay? LCA is just a tool, but it's very important that if you can do this analysis, it will break, like what I say here, to bring concepts on the implementation on storage or any other technology, because what I have developed, it has a higher impact of what I want to solve. I always explain that the first time that I was interested in this was when I was testing phase change materials in these cubicles you saw before in these houses. We were adding phase change material in the wall to decrease the energy demand of the building. But at some point, I remember asking my PhD student, okay, so we are saving 15% energy doing this, but you are adding a material to the wall of the building. So you are giving another type of impact to this building. Is the saving of energy compensating this inclusion of a new material to your building? And this is when we did our first LCA. Of course, the first one was, the answer was no. And that's, again, when it did bring us to this idea of, okay, we need to look at this more carefully. If you include a new material to a building, you need to think that maybe the material is bio-based or that it's a waste. We need to include it in a way that you can dismantle it at the end of the building. So when the building is finished, that I can take it out and reuse it, because then it's when it makes sense that I'm saving 15% energy. If not, maybe it doesn't make sense. So we have done different LCAs. Here I have an example. This was done within a European project, Highly, I think it was Horizon 2020. It finished a few years ago. But we were developing a system to store energy and to have a better energy system in buildings. It was an active system with sorption in it, and also with phase change materials. And in Lleida, we had the demo, but we also did the LCA analysis of it. We tried to, as I said, you need to see which materials you're using. This is what it's called the manufacturing stage. You need to see what are you going to do at the end of the life. How are you going to dismantle it? Are you going to reuse it? Or are you just going to dump it? And then also in the operational stage, of course, you look at how much energy you are saving compared to a standard system. And that's the other idea. To me, it doesn't make sense to do an LCA of a system by itself. You have to always do it compared to a reference system. And this is what we did. And for example, in this case, we're comparing our innovative system with a reference system. And as you can see, with the same system, using two different metrics in LCA, here the innovative system has more impact, and here it has less impact. This is using recipe. Recipe is, I will say tomorrow. So the way you count is impact points, and here it takes into consideration things like the land that you use, the safety of the system you use, and the resources. So our system was, let's say, worse than the reference one, while this one is using the global warming potential of IPCC, and here it only accounts for the CO2 emissions that you are saving. And here we were better than the reference system. I also give this example because at the end, doing the same exercise with two different metrics, you have different results, and you need to evaluate why this is happening, because to me, it doesn't make sense to do an LCA if you don't then evaluate where do you have the problem, so where are you decreasing this sustainability, so that you can give solutions. And by doing it, even with two different metrics, it can help you to identify what is the points that you have to improve in your system. As I said here, we had the pilot plan. Almatret is a very small town near Lleida, where we had it connected to a real building, and you can see all the demo, and we could really evaluate this. But from the engineering point of view, this was also a lot of fun, but it was very challenging, because to have an innovative system to heat up a real building, and the people in the building complaining, Luisa, we are hot, this conditioning is not working. Yeah, it was fun. Okay, and then finally, I have, I think, 5 minutes left. It's the social part. As I told you, the last example I gave you, it's a one clear example. Most people, if we talk only on buildings now, most people prefer to have like a heat pump or a chiller and a small boiler, because they know how it works. They think it works, everything works from the technology side, but for them, this is easy, they know it. when you come to them and say you want to put solar energy, you want to put storage, people start to get nervous because they see that the system is more complicated, that maybe they will have a problem and they will not know how it works. Maybe they have to call a maintenance guy instead of pushing just a button. So this is the idea of social acceptance. And I think that when we develop new technologies or new materials, we need to think about this and see how can we help people to understand this technology so that we can get this social acceptance. Of course, the easy way is to tell them, hey, we're getting energy independent from another country or we're being more sustainable. And there is people who is open to this. But most people at home, they don't really care about this, even if they claim that they do. If it complicates their day-to-day life, it's very difficult. So we wanted to evaluate this. And we have been doing this social acceptance thing. And another thing that we've done in social aspects is what is called the social life cycle assessment. This is a bit different to what I said before. This is evaluating in the life cycle of the production of your system is to see if social aspects are taken into account. And how is this done? If I'm talking about the life cycle of a system and of a production, you will start immediately thinking, okay, so in the production stage, it's not the final user who's involved, but it's the company that is producing this equipment. And this is what is evaluated by the social LCA. And to me, it's kind of interesting. So imagine that I have to buy PV panels, and I have two different companies selling me the PV panels. They are even very similar from a technical point of view and in cost. How do you choose which one? To me, one of the issues would be the social area, okay? And to do this, it's challenging. So there is this methodology where it's based on questionnaires. So there is a standard questionnaire developed. It's not ISO-based yet, but it's a kind of well-known standardized questionnaire. And you send this questionnaire to the company producing the solar panels. And then, oops, it tells you if they consider social aspects. Okay, which social aspects? Well, first of all, these are the guidelines that we are following. Of course, again, the full life cycle. So sometimes you have companies that only work in the installation, others only work in the operation, but others work in two of them, okay? And see that I'm looking at areas where this is more the operation, this is more the production. And these are the questions, you cannot read this, sorry, but you ask them questions about how they choose and consider their workers. So for example, you ask them, and that's why I say it's challenging, because not all of them want to answer. It's like, when you hire a person, do you prefer immigrants or local workers, okay? When you choose your vacation time, do you consider the different holidays of the different religions? Things like this, okay? Of course, you have to be a bit careful. When we do give the results, we never give at all the who answered, not even the names of the companies. Because, as you can imagine, this is very sensitive information, but at the end, it's very interesting. And to me, what is even more interesting is that when I've been working with SMEs in doing this, they tell me, oh, after we answer the questionnaire, we realize that there are many things that we are not considering and we should be considering. Okay, of course, there are the gender issues, but the value chain actors, but in the local community, you ask them, do you get involved in local community actions? Do you welcome students from schools to visit your company and to learn about what you are doing? Do you participate sponsoring science awards for schools? Okay, these are the social aspects that we ask them. We then evaluate them. We come to translate everything to numbers. We're engineers, we love to do this. And then we try to decide in your value chain of your system, which is the weak point of the social aspects of this technology. But to me, this is nice, but what is more interesting is what I said before, is working with the companies and seeing that they start to be interested in these topics because you just give them awareness of them. And I think that's, well, this is the evaluation that we did in that system that I showed you before, in the different stages of production, to use, to final disposal. For me, it's interesting to see that, you see, we saw that most companies are not taking care of the final disposal of the things that they're producing, which for me was strange because I always thought that today recycling for industry is already something done and given, and it's not. And yeah, again, we have the demo in Spain of all of this that you showed. These are the different components where we studied the social aspects and working with the companies. And for example, of course, the installers were from Lleida, so we were also asking them this questionnaire and trying to understand how they react to this. I think this is the end of my presentation. Everything that I showed is published, so you can use it. Sometimes I use this for students, so just remember to reference everything. And yeah, thank you to all the funding. We do this because, you know, some institutions fund our research, so we have to fund. We have this network on thermal energy storage that if people, some of you are interested in it, you can have a look. There is a lot of training material in here where we explain the basics of thermal energy storage. These are online courses that anybody can take. So if you are interested in it, please have a look. And then just a short announcement. We are doing a summer school on thermal energy storage in Lleida in September. The applications are open, so if you or one of your students is interested in this topic, maybe you are interested in joining us in first week of September in Lleida. In this summer school, it's the 5th time we do it. We've split between Padova, Lucerne, and Lleida. And finally, next year, we will have a conference that we do every 3 years. It's an international conference on thermal energy storage, which usually 300 attendants just on thermal energy storage, but in the widest aspect of it, sorry. So again, you are welcome to come to Lleida if you are interested. And thank you very much for your attention.
Unfortunately, we don't have time for questions, but Professor Cabezy is staying with us till tomorrow, and there will be probably many chances to talk in the, let's say, breaks about the future collaboration, because topic, I think, is so wide. There are so many people, I think, should be interested in your research. Thank you very much once again, Professor. Thank you.
Thank you. Thank you very much.
And now it's time for moving into next points of